Alright, silly people, here's the situation. This is kind of just a continuation of the last problem, where we had this funky linear combination of wave functions, um, but we added a relative phase to it. So now there's a e to the I phi uh, thing attached to the psi 2 of x in this combined wave function. And we're going to reevaluate everything that we did in the last part with this in mind. Um, So first of all, the normalization is going to be the same, and I'm going to show that off first. So normalization, you set this thing equal to 1, the integral of the mod squared over all space. Um, just expanding the square and what we have here, I'm actually going to factor out a overall a squared. We have the integral of the mod squared of the first wave function plus the integral of the mod squared of the second wave function, just like before. Um, and then we have the relative phase show up in the integrals that were 0. So this is going to be e to the I phi psi 1 star psi 2 dx plus e to the minus I phi psi 1 psi 2 star dx. Um, yeah, and evaluated from 0 to a will give you 1. The answer won't change from what we did in the last video because this integral is still 0, this integral is still 0, so the relative phase gets completely annihilated before we even did anything. So just copying what I had for the last one, um, the the normalization constant a is just 1 over root 2, and we can express now the time independent version of the wave function uh, like this here: psi 1 x plus e to the I phi psi 2 of x. We can also go ahead and write the time dependent version of the wave function, um, which is given by this general formula that I'm going to try and write out once my tablet works. Hello. There it is. That is the wave function n of x and t is equal to square root of 2 over a sine n pi x over a times this exponent e to the minus I n squared pi squared h bar t all over 2ma squared. Right. So then just plugging that into our situation, we'll get something very similar to what we did before. But now there's going to be an additional term on the psi 2 stuff. So this is going to be times exp minus I pi squared h bar t over 2ma squared. And then this is going to be root 2 over a sine 2 pi x over 2. And then in the exponent, you'll have minus I pi squared times 2 h bar t over ma squared plus I phi. That's the difference here. You have plus I phi in that exponent. Simplifying, we can write it as 1 over root a, and then using the frequency that Griffiths gave us in the last problem, which was omega equals pi squared h bar over 2ma squared, we can rewrite this stuff as sine pi x over 2 e to the minus I omega t plus sine 2 pi x over, hello, it's supposed to be an a here and an a here. Now I'm just being real goofy. A, okay. And then this is going to be e to the minus 4I omega t plus I phi. Okay. So not too different, again, from our last answer. The modulus squared is also a thing that we should look at now that we have this overall phase. And that's going to be 1 over a. We'll have sine squared pi x over a, that doesn't change, plus sine squared 2 pi x over a, that doesn't change either, but the cross terms change. We'll have a pi x over a, we'll have a 2 pi x over a. We'll have two terms which depend on this. One of them is going to be e to the minus 3I omega t plus I phi, and you're also going to have a term which is e to the 3I omega t minus I phi, right? Which, if you turn that into its exponential form, by, I'll write this out actually, that e to the I phi minus e to the minus I phi over 2 is equal to, and that's plus actually, cosine phi. So just using that formula, probably shouldn't have used phi again, but oh well. We're going to have sine pi x over a sine 2 pi x over a. We're going to have an additional overall factor of 2, and it's going to be cosine 3 omega t minus phi. So again, not too different from what we had before. There's just a phi in the cosine now, which is great for the expectation value of x, because if you remember in that calculation, we didn't really use the cosine at all during that whole thing. We just kind of pulled it out and left it in the end result. That end result being a over 2 times 1 minus 32 cosine 3 omega t, now featuring a minus phi in the cosine, over 9 pi squared. That was your expectation value of x. And if you're thinking about how that wave looks, there's no change in the amplitude. None of the constants outside of the cosine function changed. There's no change in the frequency. Because the constants on the t inside the cosine function are all the same. It's still just 3 omega. But there is a change in starting value. So depending on if you set phi to 0, which is going to be identical to what we had our result for the first time, or phi equals pi over 2, or phi equals pi, you will have different starting values for the wave, for the expectation value of x, but the wave will be overall the same. And let me actually show you what I mean by that. Okay, So what I have here is Desmos page of the different values that the expectation value will have for different phases. So this equation here is the expectation value with no relative phase. Here's with the relative phase set to pi over 2, and here's with it set to pi. And you can see, uh, given these, the amplitudes are all the same. These are all reaching the same maximum and minimum values. The frequencies are all the same. I mean, if you just look how this is looking, they're all oscillating with the same frequency even. Um, but they all cross the y-axis at different points. Uh, the green curvy line, which is with no phase, crosses at right here, which is going to have an initial value of a over 2 times 1 minus 32 9 pi over 9 pi squared. But then the one with the phase of pi over 2 crosses here at exactly a over 2. And then the last one with the phase set to pi will actually start with a over 2 times 1 plus 32 9 pi squared. Starts right there. So yeah. Also, you can change the frequencies, and it'll go wee.